Okay, I want to talk about some of our upcoming assignments, and then we'll look at some of the homework problems. So let's see, today is what, the 24th? Okay, so Faraday's law and Lenz's law, that's some of my favorite stuff all semester. Make sure you take really good notes from these videos and the ones from that Sunday here. All these Lenz's law problems, these are all really good problems. We have an Ampere's law group assignment someplace. That's the one I'm looking for. There it is. Now, all I want you to do here, because I've literally done them all for you. I've done all the different Ampere's law problems, the line, the sheet, and the slab. Here, I just want you to write them up nice and neat. So you're really just copying my solutions. So let's open this up, take a quick look at it. So draw all the appropriate pictures. So this one is the slab. This one I did for you. I just want you to, you're going to draw a picture for each one. I guess you could use this picture because they're already drawn. But you're going to discuss each line of the current, what each one's contribution is to the line integral. Write up a complete solution. Okay, this one, I guess I didn't do. I thought I had done them all, but this one we can do next time. Like I'll go through the entire thing, and then I just want you to write up with all the nice, pretty details. So make sure you take good notes from those videos. All right, let's take a look at the homework. And then we'll take a look at that group assignment that's coming up, the induced current one. Okay, so let's kind of take a step back and talk about E&M in general. So charges, if I've just got a charge sitting in space, that creates an electric field. Charges create electric fields. If you then place another charge in that electric field, it will feel a force. So some FE, some electric force, is that new charge times the existing electric field created by that original charge. Charges create electric fields. Charges interact with electric fields. Next is moving charges. So now I've got some charge here that's moving with some velocity v. That creates a magnetic field. So some b, some distance away from here, some distance r, will have b is proportional to 1 over r squared. Let's see, what is it? Q v cross r hat 1 over, I can never remember the bios of our formula here. I think we got a 4 pi on top. Let's just look it up. I don't want to get the details wrong here. The point I'm making is that moving charges create magnetic fields. But if I'm going to write it out, I might as well write it out completely, right? And I never remember if the 4 pi goes on top or the bottom. formula sheet. There we go. It's mu naught over 4 pi. Okay. So we got our mu naught here, or 4 pi here, our r squared in the bottom. So moving charges still create electric fields because they're charges, but they also create magnetic fields. Now you place another charge in here, some charge 2, that's in here. If that charge is stationary, he's going to see the electric field, but he's not going to see the magnetic field. Only moving charges notice magnetic field. So let's put him moving with some velocity vector. Maybe we'll call that V2 here. Then he'll feel, of course, his electric force, K, Q1, Q2, over their distance. So maybe that's R now, squared in magnitude. And then there's a magnetic force. I never remember if we have a mu naught here. No, just Q. V cross B. So I call that V2 cross with the magnetic field this guy caused. Moving charges create magnetic fields, and other moving charges are affected by magnetic fields. Later on, we're going to take it one step later, or one step further. So stationary charges create electric fields, moving charges create magnetic fields. What's after velocity? Acceleration. Accelerating charges create electromagnetic waves. Light. Light is caused by accelerating charges. If you take a charge and you wiggle it around, you create light. That's all light is electromagnetic waves. Okay, so if I have a current, that's a bunch of moving charges. That creates a magnetic field. So a current by itself, I've got some current here, just existing in space. I'm not to the problem yet. This is not the homework problem. Just a current is a bunch of little charges moving with velocity v up that way. Well, that will create a magnetic field perpendicular to the charges. And the easiest way I found to figure out directions is anytime something's going straight, use your thumb for the straight one and you curl your fingers for the curly one. So for example, I think I'm gonna need my camera. Let me pull up my camera. And that, see if that turns on properly. Okay. So if I've got some current flowing in that direction, like that, then I'll point my thumb in the direction of the current and my fingers will curl around like this in the direction of the magnetic field. So the magnetic field curls around. Let me make sure I'm sharing. If I hit stop share, that'll get it there. Okay. So if a current's flowing that way, the magnetic field will curl around it. So if I had a magnetic field from, say, a current coming straight out at us, so that's some current flowing out. That's moving charges. It's flowing straight up towards your eyeballs. My fingers curl around like this. The magnetic field from that current, I'll get B lines that go around in circles. If I had a current flowing like this, here's I. Then current's flowing that way. Over on this side, my magnetic field is flowing into the board. Remember, that's how we draw a vector that says into the board. Back behind, underneath my desk here, the magnetic field will be flowing to the left. Over here on the left side, the current is flow, or the B is flowing out. Up here on top, B would be flowing to the right. So it's going around in circles around I. So that's the magnetic field caused by a current. If on the other hand, say I have a current that's flowing in a circle, so maybe my current is doing the circle one, like a solenoid. So my current is the circly one. Then I use my fingers to do the circly one, and I'll let my thumb do the straight one. I'll get a magnetic field that points straight out. B will point out if I goes in circles. So a classic example of that, like in your car, your solenoid on your car, is a loop. It's got a metal rod in it, but forget about that right now. So this is going like this. It's like a spring. So if I point my fingers in the direction of current, the curly one, the one that's curling around, it's curling like this, my thumb will point in the direction of the straight one. So we would get a magnetic field inside here that's approximately constant and points to the right. Moving charges create magnetic fields. Whenever one of them is curly and the other one is straight, use your right hand rule and let your fingers curly the curly one and straight one, your thumb will straight the straight one. Okay, now that's not the problem we have. Let me share, and I gotta switch back. Probably could plug it both of these in at the same time. Are we? Oh. So I've got some current that exists in an already existing magnetic field. So this guy's creating his own magnetic field that's going to interact with the field that already exists. So we could find the interaction between these two magnetic fields, or I could think about individual charges flowing there and think F is going to be Q times V cross B to figure out the force, or that's already been solved for me. I could figure out, or I could just use this formula. This is the force on a wire in a magnetic field that already existed. Okay, so this is up another level. I've got moving charges in a current. They're creating their own magnetic field that's interacting with this B that already exists. We want to figure out the direction. So we're using this formula. F is I times this vector that points in the direction of current crossed with B. So let me try and see if I can plug both of these in simultaneously so I can go back and forth. I don't know if I have enough. Yeah, this might work. Okay, so start video. Okay, so I've got some current that's flowing up. I need a better marker. I've got a magnetic field that points out of the board. That's B. Maybe I should have done that in a different color. And we're going to use F vector equals I times this little L vector that points in the direction of current crossed with B, and right-hand rule. So I'm going to point, some people like to do the 3-finger method like this. They just hold their hand in this orientation. I like to do the curly method. So I'll do it both ways. Start with I, point my fingers in the direction of I. I have no idea which way my hand goes yet, but I know my fingers point towards I. Curl in the direction of B. That's the second one. I cross B. B's pointing that way, so I need my fingers, see my fingers curl. No, B points up. So I need to rotate my hand, I cross B. Then my thumb will point to the right. Or if you like the 3-finger method, I, B, I, B, F. So F, the force on this wire will point to the right. So the answer there is to the right. Okay, you can play with this one. We got a current flowing. Current always flows from positive to negative. So the current's going to be coming out this way. Okay, that's a good one. Think about that one. I don't want to do all these for you. Okay, that one has a written example. That one has it written. Yeah, see, not sure we need a lot. Yeah, and with the videos we already have, I'm not sure I need to do any more of these. I think that should be good. Make sure you take good notes from all the other videos. If you have any questions, feel free to send me an email. I'll be happy to do more of these. I think we should be good. That's a good place to stop.